Good morning, ma'am. This is Bhavana. I am from Computer Science and Engineering Department. Today I am here to give a presentation on my topic, and my topic is Q networks, deep Q networks, and policy optimization. Reinforcement learning is a powerful branch of artificial intelligence that helps machine learn by interacting with trial and error. The agent performs an action, receives a reward or penalty, and then adjusts its behavior to maximize future rewards. The main goal of reinforcement learning is to learn an optimal policy, like a strategy that tells the agent what action to take in each state or each situation to achieve the highest long-term rewards. Components of reinforcement learning. The basic components of reinforcement learnings are agent. It defines the learner or decision maker. Example like robot or AI system. Environment defines the world in which the state of agent operates. State is represented as S. It defines the current situation or condition of the environment. Action represented as A. It defines the choice available to the agent. Reward or it defines the feedback the agent gets after taking an action. Policy is represented as pi. It defines the mapping from state to action. Value function the expected total reward from a given state. Example, a robot navigates maze through each step in a action and reaching the goal gives a reward. The robot learns to find the fastest path. What is Q-learning? Q-learning is one of the most popular and simple algorithms in reinforcement learning. It is a model-free method. It means it doesn't need to know how the environment works. Q-learning tries to learn a Q function represented as Q of S of A, which gives the expected cumulative reward for taking action. A is action and state is S, and the following best possible policy afterwards. The Bellman equation is represented as Q of S of A equal to Q of S of A plus alpha of R plus gamma max of Q of S dash comma A dash minus Q of S comma A. Here alpha represent learning rate and gamma is equal to discount factor or is reward. S dash is next state and maximum of A of S is best future reward. Limitations of Q-learning. Q-learning works well for small problems, but when there are too many states or actions, it becomes slow and intelligent because it uses a Q table to store the values. It fails to generate between similar states and it cannot process high dimensional inputs like images or sensors, and it requires maintaining the large Q tables which grows exponentially with the number of states. Introduction to Q networks. To overcome these limitations, researchers introduced Q networks. A Q network is a neutral network that approximates the Q function. Instead of storing Q values in a large table, the network predicts Q values for all actions given in the current state. Input refers current state can be vector or image. Output refers a Q value for each action. Parameters represented as theta. It defines the weight of neutral networks. It mathematically represents Q of S comma A comma theta similar to Q into S comma A. Terms theta represents network's weight, Q into S of A optimal Q value for state S and action A. This approach helps generalize between similar state and work even for large or continuous space like image or sensor data. A Q network is a type of neutral network. And how Q network works? Observe the current state from S from the environment. pass S through the neutral networks to predict Q values, select action with highest value, perform actions and rewards, receive rewards or update networks weight theta using backpropagation. Deep Q learning is also known as DQN. DQN is an advanced version of Q learning that combines deep learning and reinforcement learning. It was introduced by DeepMind in 2015 and became famous for achieving human level performance on Atari video games. Key ideas are use con- convolution neural networks to process complex input like game frames. Learn Q values automatically from raw pixels. Use smart technologies to make training stable. And first step towards general artificial intelligence. DQN equal to Q learning plus function approximation plus deep networks. Stabilized training with experience, reply and target networks. End-to-end reinforcement learning approach and quite flexible. Key concept of DQN. Components are three types: experience replay, target networks, and greedy policy. Experience replay means store past experiences in a replay buffer as like action, state, reward, next state. During training, random samples are taken from this buffer. This breaks correlation between consecutive samples and improves stability. Target networks defines a separate copy of Q networks is used to calculate target values. Updates updated less frequently to reduce oscillations and stabilize learning. Greedy policy defines balances exploration and exploitation with probability epsilon. Choose a random action, otherwise choose the best predicted action. Benefits are more scalable, more stable learning, better generalization, handle large or complex environment efficiently. DQN algorithms. Steps in DQN algorithms are initialize replay memory and queue networks with random weights for each episode. Select an action using epsilon naught greedy policy. Execute the action and observe reward and next state. Store SA or S in replay memory. Compute target Q values using target networks. Update the Q networks using back proportion. Update target network weight. Through this process, the agent gradually learns the best strategy for maximizing long-term rewards. Policy optimization. Now let us move to another major strategy of our reinforcement learning algorithm, policy optimization. Instead of learning key values, these methods directly learn the policy which represent the probability of taking action A in state S. The goal is to maximize the expected total reward. Terms theta defines policy parameters or defines total reward accumulated from following policy pi. Phi theta of A comma S defines probability of taking action A in state S. It is represented as J of theta equal to E pi theta into E of R. Policy gradient algorithms. It optimizes policy parameters theta using gradient ascent. Reinforce algorithm. It is uses policy gradient to improve policy directly. Actor critic methods. It combines the value based and policy based approaches. Actor chooses actions like policy networks. Critic evaluates how good the chosen action was. Policy optimization is a modern, stable policy gradient algorithm widely used in robotics and control systems. Actor critic architecture. Actor chooses action based on policy. phi of a or s comma theta. Critic. It evaluates action using value function. Function is represented as v s comma w. Critics feedback improves actors policy theta, helps stabilize learning and accelerate convergence. Application. Reinforcement learning is used in many real-world domains like gaming, robotics, autonomous vehicles, finance, and smart agriculture. Gamings like Atari, SAI, Dota 2 bots, AlphaGo, and robotics like arm control, working robots, navigation. Autonomous vehicles like lane following, obstacle avoidance, finance like trading, portfolio optimization, smart agricultures like crop monitoring and automated irrigation. These applications shows how reinforcement learning helps machine learn complex behavior through the experience. Conclusion. To summarize, this reinforcement learning teaches agent through interaction and feedback. Q-learning provides the foundation for value-based reinforcement learning. Q networks and deep networks over the limitations of Q tables using neutral networks. Policy optimization directly learns decision-making strategies. Actor critic and PPO methods combine both words for efficient, stable learning. These algorithms power, power many of today's intelligent systems, from self-driving cars to game-playing AIs. Finally, reinforcement learning is a step toward true artificial intelligence, where machines can learn, adapt, and make decisions on their own, just like humans do through experience. Thank you, ma'am.